Okay, we're going to start this lecture by talking about heat. This is, as you can see, a rather robust lecture, contains a lot of topics, but they all revolve around the idea of heat. At the end of this lecture, we will go beyond that and we'll introduce the first law of thermodynamics. But let's start first by talking about heat and what it represents. Alright, so here's the definition. You might have heard this from former science classes, perhaps physics, but heat is nothing more but a form of energy. And as such, we've probably already seen many aspects of energy in the form of heat before. Like we're seeing here on the picture of an erupting volcano with the molten lava, or we also have casting irons in very high temperatures in order to be able to actually mold it to the specific shape required for the manufacturing process. Fires, some of them creating in grills, um, are also an example of heat. And you guys have used a Bunsen burner in the past, so you know that just by providing a little bit of fuel to oxygen, you can end up generating enough heat out of a reaction. And speaking of that, temperature is actually our best measure of heat. Anytime that we use a thermometer, what we've been basically measuring is the amount of heat contained within a substance or in the environment as a whole. And the interesting thing about heat is that it can actually be produced by chemical reactions. And some of them don't even need to be chemical. One of the best sources of heat that issues itself as an energy source, a fuel, if you will, for spacecraft is plutonium-238, shown here on the bottom right corner. What you can basically see is a glowing red piece of plutonium-238 that is so radioactive and technically so hot that it produces substantial amount of heat that can be used as the source of energy to propel spacecraft into outer space. And the other key that we're going to investigate, although this will be mostly allocated to the next lecture, will be the fact that heat, being a form of energy, can actually be exchanged with potential energy. And potential energy, unlike heat, is energy that can be used to do some type of work on a system, whether it's mechanical or chemical, depends on the system itself. But heat can go back and forth between this, potential energy and kinetic energy, which is what heat is. All right, so let's focus first on the first two entries. So heat is energy and temperature can be used to measure heat. Let's take a look at that. All right, so in the case of temperature, you may recall from our gas lecture, specifically the kinetic theory of gases, that given a volume of space in which gases are moving about in all three directions, x, y, and z, we find out that pressure times volume equates to a third of the mass of the gas particle multiplied by its own speed square. But we also know that the kinetic energy of the gas is 1/2 mv squared. So simple substitution will show us that the kinetic energy is simply 2/3 of the value of mv squared times 1/3. In other words, the 3 on the top of this fraction and the 3 on the bottom of that fraction will cancel out to give you simply 1/2. In other words, 1/2 mv squared. But because 1/3 mv squared corresponds to PV, technically speaking, we're looking at kinetic energy being 3/2 of PV. And PV, since we're dealing with a gas and we're assuming it to behave ideally, PV can be substituted with nRT. And lastly, this we saw in the previous lecture, if we divide both sides by the number of moles, we actually get the energy per mole, which is 3/2 RT. Now, the big idea right here, and the reason why I'm restating this process of deriving the kinetic energy as a result of temperature is that heat is actually kinetic energy. In the previous set of slides, I mentioned that potential energy and heat can go back and forth, and the reason why is because heat is best associated with kinetic energy. So the fact that the kinetic energy in this equation, for a gas at least, is given by and interpreted solely by the temperature at which the gas is held, tells you that heat can definitely be measured with temperature, right? Because after all, heat is nothing but another outcome of kinetic energy. And when you think about molecules, you can actually think about the fact that heat is now being correlated to the collisions of these gas particles. The higher the temperature, the higher the collisions, and the faster the speed is, and the more dramatic these collisions can actually be. In some cases, just by raising the temperature can allow you to undergo chemical reactions that at lower temperatures wouldn't have happened, anyway. All right, so let's take a look at this idea of the gases, pressure, and heat, and we're going to correlate this to some of the 2D gas laws that we talked about in lectures 8 and 9. All right, so once again, the heat is correlated to the temperature of the gas, right? Now, higher heat implies that you're going to have higher temperature, and that's simply because heat is the same thing as kinetic energy, and kinetic energy is given by the amount of temperature at which the gas is being held. But since the heat is correlated to the number of collisions of gas particles, what this means is that higher temperature or higher heat is going to ultimately come down to higher collisions, higher number of collisions, and collisions that have higher energy and momentum associated with them. So you're going to have a higher force of impact for these gas particles colliding onto the walls of the container. And the interesting thing is this, because pressure is the same thing as force over area, the higher the heat, which means higher temperature, which means higher collision, which means higher force, the higher the heat, the higher the overall pressure. Just by the fact that we're increasing the force, we have to increase the pressure. And check this out. Now we have a relationship right here. As we increase the pressure, we do increase the temperature. And that you may recall as nothing more than Gay-Lussac's law. Increase pressure, increase temperature. Decrease pressure, decrease temperature. That's literally what the interpretation from the point of view of the collisions of the gases tells us. So Gay-Lussac's law is a direct corollary of this aspect of kinetic molecular theory. And moreover, if the gas that we have is contained in a receptacle that can actually expand or compress at will, so you have a removable or expandable rather stopper right here, movable stopper, when you increase the heat, once again you increase the temperature, and that once again correlates to the higher number of collisions that a gas particle can have and collisions that carry even more momentum. So what's going to happen is that the higher collisions are going to generate higher force, and if it so happens that this flask contains a movable piston, the piston, upon interacting with a higher force, will expand in volume. It'll actually be raised up by the mere force of the gases colliding against it. So what this will actually allow to happen is that the volume inside the flask will expand. And check out what we've just done. We said that if we increase the heat, aka if we increase the temperature, ultimately we're going to increase the volume of the gas. And that's nothing more than Charles' law stated in equation format, but now represented by the collisions of the particles and kind of correlating the idea of heat to how the gases are ultimately affecting their surrounding. All right, now the last thing to discuss is the units of heat. And heat initially was determined and rather associated with water. So here we have an Erlenmeyer flask on top of a hot plate, and we have a thermometer measure the temperature of the water. The water initially being held at 22 degrees Celsius. If you start heating up the flask, right, so you start generating heat with a hot plate, and you start monitoring the temperature, the amount of heat that it takes for the temperature of the water to increase from 22 to 23 degrees Celsius, in other words, to increase by 1 degree Celsius, is what we call the calorie. All right, and specifically, this is done if you're dealing with 1 gram of water and the temperature changes only 1 degree Celsius. That amount of heat delivered to the 1 gram of water is what we call the calorie. Now, as cute as that sound is, and as ubiquitous as it is in daily life, we see that in nutrition labels everywhere. The truth of the matter is that it's not an SI unit. And so here's where the physicists kind of come in and help us out. So here you can see that there is a 1 kilogram weight attached to a pulley system, and the pulley system itself is attached to a steel rod submerged in a pool of water. And once again, this pool of water has a thermometer measuring its temperature. So if you have a block dropping from about 43 centimeters, so you let go of the drop, the block is going to start dropping down until it hits the ground, and it will take about 43 centimeters worth of height to reach the ground. In the process of this, the pulley system steered the water in which it was submerged, and the gravitational energy was basically turned into potential energy or mechanical energy that ultimately leads to an increase in the temperature of the water. And by doing this measurement pretty well, you can actually determine the energy delivered to water. And now here's how the equation goes. The energy delivered was equated to the gravitational force, which is the mass of the object times the gravitational constant times the height the object was being held. So we have a 1 kilogram object, which is multiplied by 9.8 meters per second squared, gravitational constant, multiplied by 0.43 meters, which is the height at which the object was being held. Now, if you do the calculations, you're going to find out that this equates to 4.184 kilograms meter square over second square. And this is the amount of energy delivered if you have 1 gram of water raising up by 1 degree Celsius. It turns out that in order to deal with all these crazy units, we call the kilogram meter square second square the joule. And so we say that 1 joule has been, 4.184 joules of energy have been delivered to the water, the 1 gram of water. And what it also tells us is that 1 calorie equals 4.184 joules worth of energy. All right, so in the next video, we're going to talk about the specific heat capacity.